Hi, I'm Valentin Antuori, and in this video I will present a work about using the Monte Carlo tree search algorithm to solve a scheduling problem. Surely, if you are interested in AI and games, you already have heard about the Monte Carlo tree search, so MCTS for the rest of the presentation. So at first, MCTS was developed for the game of Go and really shined in 2016 when Google DeepMind's bot AlphaGo, which is based on a Monte Carlo tree search algorithm, uh, mixed with neural networks. So this bot beat one of the most talented players, Lee Sedol. Basically, the MCTS can be seen as a kind of a best first search, but guided by samples and mixed with a multi-arm bandit algorithm to explore the tree. And it is a repetition of four phases. The selection phase, where the goal is to select a promising node to expand by traversing the tree from the root using multi-arm bandit procedure. Second, the expansion phase, we will expand that selected node. The simulation phase will play a rollout from that newly expanded node. At start, the rollout in the context of games was simply playing random moves until we reach a final state. And finally, the outcome of this rollout, a win or a loss in the game, will be backpropagated to the newly created node and all its ancestors through the root node. And this information will be used for the future selection phases. So we decided to use this algorithm to solve a scheduling problem. So first, I will introduce this problem, explain why we thought this algorithm would be good, and then I will describe deeper the principles of the MCTS when it is applied to a combinatorial optimization problem and the adaptations we made to obtain good results for our problem. And finally, I will show some experimental results before concluding. So we are interested in planning moves of vehicles components across an assembly line. We have logistic operators who are in charge of collecting components from their production station and delivering them to their consumption point. Here we only deal with a single operator case. So we have only one operator. And these components are carried over using trolleys like this one. And each trolley is specific to a component. So those trolleys can be stacked into a train, which is bounded in length. So this is a constraint. And the problem, globally, the problem is to move these trolleys when they are full from their production point to their respective consumption points, and symmetrically to bring back them when they are empty. So this is a special case of a single vehicle pickup and delivery problem with time window and with a capacity, which is the maximum length of the train. A particularity of that problem is that each request is cyclic. For example, if I take a request, its due date corresponds to a release date of the same request, exactly the same, at the same place, but shifted in time. A representation of a solution for this problem is a sequence of the n operations. So an operation is either a pickup or a delivery. And this sequence must respect three constraints. So the operations must occur in their time windows. Each pickup must precede its delivery, and the constraint on the train must be respected. So originally, the problem is a decision problem with hard constraints. We want to know if an assignment of a set of machines to an operator is valid. But here we will work with a minimization problem by relaxing the constraints on the due date and minimizing the maximum tardiness. And if the objective is 0, we have a solution for the read problem. So previous experiments show us that with a good heuristic, it is sometimes and surprisingly possible to find a solution with some greedy runs of the solver we used and with an aggressive restart strategy. Then the MCTS seemed to be a good approach as it strongly relies on many rollouts. So first, some generalities about the MCTS. So each node in the tree represents a state of the problem. An arc between two nodes is a feasible decision, and a final state, a leaf, is then a solution or a contradiction. For our problem, we represent our sequence of operations along the tree. Then the root is the empty sequence, and a decision is the action of extending the sequence with an operation without breaking the constraint. And for each node, we store some informations. First, the number of visits since the start of the algorithm, a prior probability or preference to choose this node from its parent that I will explain later. And finally, we have to store its current evaluation. So what is an evaluation? In game, the evaluation of a node is easy and is based on the win-loss ratio we got in the previous rollouts, and we backpropagated to this node. So in combinatorial optimization, we usually don't win or lose a game. There is one paper who consider an improving solution as a win and base its evaluation on that. But we know we will find lots of improving solutions at the beginning of the search and only a few ones after. So it is certainly better to use an evaluation based on the averaged objective value, and this is what most papers that use the MCTS do. So we use something a bit different in this work. We assume we can have a lower bound on the objective value after each decision, and we define a penalty of taking this decision by the marginal increase of the lower bound. So our evaluation of a node is then the averaged sum of marginal increment of the lower bound from this state in the long run. So it is based on the value of the objective function, but this function is not only evaluated at the end of the rollout. And the exponential decay was added because we deal with long horizon and we don't want to penalize an action with some bad decisions which can be taken a long time after. Okay, now I will focus on the four phases I mentioned before. So first, the selection phase. So this phase begins at the root node, and we will successively choose the best child following this equation until we reached a leaf. So in the first rectangle, we have what is called the exploitation term. And here we have the evaluation of the node reached when taking the decision O in state sigma. And on the right, we have the exploration term, which give a bonus that decreases with repetitive visits. In the literature, there are several variations of this term, but we use this one, which is used in the AlphaGo, because with this one we can have the prior probability, and this probability, this preference, allows us to put some built-in knowledge in the algorithm to bias the exploration. So finally, the two terms are balanced with a coefficient C, which determines a compromise between exploitation and exploration. And therefore, it is easier to tune this parameter when the exploitation term is normalized. So we normalized between -1 and 1. So we modified a bit the behavior of the native algorithm for the selection phase. So preliminary experiments show lack of deep exploration for instances with a large horizon. So usually in the regular MCTS, you will find that I call a commit here. So in game, after a small timeout, the computer must play. Then it have to choose one child at the root node, the best child at the root node. So in combinatorial optimization, you can do the same. So after a timeout, you can commit the best decision at the root node and continue the search after. And you keep the tree behind this node you just choose. But we think this timeout is a parameter that is hard to tune. So we propose instead a dynamic compromise, which will perform a kind of a soft commit, and it will force the exploitation on the higher part of the tree as the tree grows. So the C parameters will be dynamic depending on the size of the tree and the current depth or step of the selection. So at depth T of the selection, we multiply the C coefficient by this parameter beta to the power of the tree depth minus T. So after that, we have the expansion phase. So we propose to add all the children of the selected node at once. And we initialize the visit counts, the evaluation, and we define here the prior preferences. So these preferences must be in the form of a probability distribution over the children. And if you don't have such a distribution, you can use a uniform distribution. So for our problem, we have a fitness function for each child, which is a simple linear combination of 4 criteria. The distance of the operation from the current place, the emergency according to the due date, and 2 static criteria, the length of the trolley and the type of operation, which is either a pickup or a delivery. And we turn this into a probability distribution with a softmax function. So the simulation, in this phase, the goal is to extend the partial solution we have at the selected leaf to a complete solution. Here we can use any greedy randomized algorithm we have, and our is based on the same fitness function I just mentioned. However, we have to keep track of the growth of the lower bound at each decision in order to compute our evaluation. And in order to have an intensification of the search, we propose to use a backtrack limited depth first search instead of the rollout. So how it works, first we make a regular rollout until we would have a fail with our bounds on the objective function. Then we have to evaluate this rollout when we have the fail. If it is a good one, the budget will be great. And if it is bad, the budget will be small or null. So for our problem, this evaluation is based on how far we have come without lateness during the first dive. And if we did not have a fail, then we just found a new solution. So great. And the budget will be then maximum. Finally, when the budget is fully consumed, if we don't have a full solution, we extend the best branch we found to a full solution using the heuristic. And finally, the backpropagation. So in this phase, we have to backpropagate the growth of the lower bound through the path from the selected node sigma to the root. So first we compute the sum of marginal increment of the lower bound we got from the rollout with the exponential decay. And then we have to add the growth of the lower bound when we took this decision from the parent of sigma. And we update the node information, so the visit count, the evaluation with the outcome of this rollout, and we repeat this step until we reach the root node. Okay, so we did some experiments and we compared different versions of the algorithm with the result of previous work. So our baseline is made of 2 algorithms. The first one is a CP model which deals with the satisfaction version of the problem. And the second one is a multi-start local search. And both methods using the same heuristic based on the 4 criteria. I will show only the 2 best versions of our algorithm. both using the three additions we made to the regular MCTS, so the evaluation function, the DFS, and the dynamic compromise. The second algorithm is a bit different than the first one because it tries to solve the satisfaction version of the problem, but only during the DFS phase. So we generated 4 classes of instances which are available online, and in each class there are 10 sets of components, and each one is declined in 3 time horizons. The shift of an operator of 7 hours and something, a day made up of 3 shifts, and a week of 6 days. Then there are in total 120 instances. The easiest has about 600 operations, and the hardest about 14,000. We run each algorithm 10 times during 1 hour, and you can see here a bunch of parameters for the method. So the results, we have the 4 classes, A, B, C, D. For each one, we have the 3 time horizons, and then each line corresponds to 10 runs on 10 instances for each of the 4 presented methods. So we are interested in the number of instances solved, that is an instance with a solution with no tardiness at all, and the averaged maximum tardiness. So in global, we can see the 2 MCTS methods globally solve more instances than the CP approach and than the local search, up to 9.5%. And if we look the objective function, the maximum tardiness, both MCTS outperform the local search. In detail, we can see that improvements are really focused on the shift horizon and day horizon, but no methods really outperform CP in the week horizon. And finally, we can see that 50% of the instances remains unsolved, but we are pretty confident that a large part of them are in fact infeasible, especially for the weak horizon, because we have no guarantee on the satisfiability of the generated instances. So to conclude, we applied the Monte Carlo tree search to an industrial problem, and this approach improves the results of the previous method. And I didn't show the table that prove the third point, but we identified the benefit of the 3 components we had, our evaluation functions, the DFS, and the dynamic compromise. And the 3 components improve the result of the native method in general, and especially for the day and week horizons. So we developed this approach for one specific problem, our trolley problem, but this method remains generic, and we want to highlight this in future works. In fact, we are currently working at expanding these experiments on 2 other problems, a job shop problem and an industrial bin packing problem. And for the job shop problem, we try to hybridize the MCTS with a CP solver. Then all the simulation and the rollouts and the DFS will be made by a CP solver. So thanks for watching this presentation.